On December 13, 2025, at morning twilight, the Subaru telescope on Mauna Kea turned its 8.2-meter mirror toward a single coordinate in the constellation Cancer. The target was designated 3 Atlas, the third confirmed interstellar visitor to cross into our solar system, and the observation was routine in protocol but unusual in circumstance. Within hours, multiple independent teams across 3 continents reported the same pattern. The object's brightness behaved as predicted for its distance and phase angle, tracking cleanly against standard dust scattering models. Yet the spectroscopic signatures that should have accompanied that brightness, faint emission lines from hydroxyl radicals, subtle color shifts in the dust continuum, even the expected phase response in polarimetry, didn't align in the most fundamental ways. The discrepancy was not dramatic. It was the kind that makes seasoned astronomers stop treating an object as cataloged and start treating it as a question that refuses to resolve. By the 19th of December, when 3A Atlas reached its closest approach to Earth at 1.7 astronomical units, roughly 250 million kilometers, telescope time had been reshuffled across observatories in Hawaii, Chile, Arizona, and the Canary Islands. Networks that usually operate independently synchronized their cadence. The object became a shared target. The mystery wasn't what is it. The object had been confirmed as interstellar 6 months earlier, on the 1st of July 2025, when the Atlas Survey telescope in Chile caught a faint smudge moving at 57.7 kilometers per second relative to the Sun. Velocity too high for any object gravitationally bound to our star. Pre-discovery images traced its path back to mid-May. Its orbital eccentricity of approximately 6.139 left no ambiguity. This was a visitor from another stellar system, inbound on a hyperbolic arc that would carry it past the Sun and back into the interstellar void. What unsettled the observers in mid-December was simpler and more unsettling. The data was refusing to agree in ways that made no sense unless something fundamental about the object, or the way it was interacting with sunlight and the solar wind, was not behaving like the models predicted. The watch intensified not because 3A Atlas announced itself with spectacle, but because the geometry and timing created a vanishingly narrow opportunity to measure things we usually miss. Interstellar objects move fast. They appear, brighten, fade, and recede into the outer solar system on timescales measured in months, not years. Oumuamua, the first interstellar visitor discovered in 2017, left the inner solar system before anyone fully understood what it was. A small, elongated body that showed no detectable coma, no gas emissions, yet exhibited a tiny, non-gravitational acceleration away from the Sun that defied simple explanations. Toy Borisov, discovered in 2019, behaved more like a classical comet. Active, gassy, observable. But it was never seen at phase angles smaller than 16 degrees, meaning critical measurements of its dust properties, especially the opposition surge, a brightness spike that occurs when the Sun, object, and observer align almost perfectly, remained out of reach. The astronomy community learned from those encounters. Don't waste the window. Don't assume the object will cooperate. Don't let a visitor slip away with more questions than answers. For 3I Atlas, the window is different. The object passed perihelion, its closest point to the Sun, on October 30th, 2025 at 1.356 astronomical units, closer than Mars but farther than Earth. That proximity triggered outgassing and dust production as expected. But the real opportunity wasn't perihelion. It was what happens next. On January 22nd, 2026, just 1 week from now, 3 Atlas will align to within 0.69 degrees of the Earth-Sun axis. For approximately 7 days, centered on that date, the phase angle, the angle between the Sun object line and the Sun-Earth line, will remain below 2 degrees. This is opposition geometry, the configuration where shadows vanish and light scatters back toward the observer with maximum efficiency. For most solar system objects, this alignment produces a nonlinear brightness surge driven by 2 physical effects: shadow hiding at angles larger than 2 degrees, where particle shadows disappear behind the particles themselves, and coherent. Backscatter at angles smaller than 2 degrees, where light traveling reciprocal paths through dusty media interferes constructively. The amplitude and width of that surge reveal the albedo, structure, and packing density of dust grains, whether they are compact and thermally processed or fluffy fractal aggregates, whether they are carbon dark or ice bright. For 3I Atlas, this will be the first time an interstellar comet has been observed in this geometry. The chance may not repeat for decades. And so the object has become a time domain target, less a photograph, more a heartbeat the community is trying to interpret before it fades. But the coordination runs deeper than opportunistic scheduling. Beginning in August, spectroscopic observations from the University of Hawaii's 88-inch telescope captured the earliest blue-sensitive spectrum of 3I Atlas, obtained just 12.5 hours after the discovery announcement. Those early spectra revealed a developing coma, a diffuse cloud of gas and dust, and confirmed cometary activity. By late September, Gemini North images showed a greenish glow consistent with carbon-bearing molecules. Yet, as the monitoring campaign extended through October and November, a pattern emerged that resisted easy interpretation. Photometry suggested one narrative: brightness increasing as the comet approached the sun, consistent with sublimating ices releasing dust into the coma. The rate of brightening was steep, following a power law close to solar distance to the -7.5, faster than typical comets, but not unprecedented for objects undergoing rapid outgassing. Spectroscopy, however, suggested a different story. Observations with the Very Large Telescope in Chile and X-shooter spectrographs detected unexpectedly weak or absent emission lines in wavelength ranges where even modest volatile activity, water, hydroxyl, cyanogen, should leave a trace. In some cases, upper limits were set. The flux within key spectral bands fell below 3 sigma detection thresholds, meaning if gas was present, it was orders of magnitude fainter than the brightness alone would imply. This created what observers began calling a contradiction map. Not a single headline anomaly, but a structured set of inconsistencies where every measurement was plausible in isolation but uneasy together. Astrometry added a third layer. Long baseline measurements tracking the object's position over weeks and months revealed tiny deviations from a purely gravitational orbit. Non-gravitational accelerations consistent with rocket-like forces from outgassing jets. Such accelerations are common in comets. Sublimating ice releases gas that pushes the nucleus slightly off course. But the magnitude and timing of the acceleration in 3I Atlas raise questions. Early analyses estimated a mass of approximately 44 million tons, equivalent to a carbon dioxide-dominated nucleus radius of less than 374 meters. If that mass estimate was correct, the observed acceleration implied a specific rate of gas loss. Yet the spectroscopic non-detections implied gas production far lower than that rate would require. The numbers didn't fit. Either the object was producing gas in a compositionally unusual way, perhaps dominated by species like carbon dioxide or carbon monoxide that don't emit strongly invisible light, or the surface was changing in ways that decoupled brightness from gas production, or the acceleration was being driven by processes that don't follow the standard volatile sublimation playbook. In mid-November, a coordinated observing run targeted the most revealing test, searching for faint molecular emissions during a high-value geometry window, when the comet's orientation and solar illumination should maximize detectability. Multiple facilities participated: Hubble Space Telescope, the Green Bank Radio Telescope, the Allen Telescope Array, and ground-based optical spectrographs in Arizona and Chile. The goal was to push detection limits down to levels where, if standard cometary processes were driving the brightness, at least some trace of water vapor, hydroxyl, or cyanogen should appear. On December 19th, when 3I Atlas made its closest approach to Earth at 1.70, the Green Bank Telescope conducted a 6-hour observation sweep across frequencies between 1 and 12 GHz, searching for narrowband radiards emissions that might indicate artificial signals or unusual molecular lines. The Allen Telescope Array followed with multi-band monitoring. The results came back unusually clean. Upper limits, non-detections, flat baselines where small signals would have been expected. The spectroscopic silence was not absolute. Some detections were made, including surprising nickel vapor emissions and incipient traces of cyanogen at large heliocentric distances, but the overall pattern was one of constraint, not confirmation. If the object was active, it was not behaving like the simplest version of what brightness means in cometary science. Non-detection, in this context, is not failure. It is data. It proves the object is not conforming to the standard template. Scientists began treating the upper limits like boundary conditions in a physics problem. If there is activity, it may be compositionally unusual, episodic, geometry-dependent, or happening in wavelengths and timescales that hide from common tracers. The watch grew more intense because the object was forcing the community to measure what was missing, not just what was present. Silence, in astronomy, can be as loud as signal if you know how to listen. By late December, another disquiet surfaced, a sense that events were happening out of order. In ordinary small-body physics, heating from the sun, rotational tumbling, and outgassing follow recognizable schedules. An icy comet at 3:00 begins sublimating water ice. As it moves inward, carbon dioxide and carbon monoxide become dominant. Near perihelion, activity peaks. Afterward, as the comet recedes, brightness fades smoothly, and gas production tapers off in a way that correlates predictably with solar distance and rotational phase. But the latest time series photometry and spectroscopy of 3 Atlas hinted at mismatches, subtle shifts in brightness or scattering properties that occurred without the expected thermal lag, or with lags that didn't fit thermal inertia models. If the surface was changing, perhaps fresh ice exposed by dust ejection or crust formation suppressing volatiles, why weren't the usual molecular signatures following those changes? If the object was rotationally stable, why did time series measurements show small but persistent departures from smooth light curves? Some observers noted a 2-to-1 elongation in the coma shape, a symmetry inconsistent with steady outgassing from a uniformly active nucleus. Others documented an anti-tail, a narrow jet of material pointing toward the sun, opposite the main dust tail, suggesting episodic bursts or structurally complex dust release rather than continuous sublimation. Scientists began comparing timestamps more than images. They searched for correlations. Did brightness changes track solar wind conditions? Did spectral shifts coincide with rotational phase, assuming the nucleus was tumbling? Did astrometric accelerations pulse in sync with coma brightness, or were they decoupled? The object became a timeline problem. Not one anomaly, but an ordering of events that refused normalization. And because the object was receding, already beyond 3:00 by early January, magnitude 16.7 and fading, the opportunity to resolve these questions was narrowing every day. The January 22nd opposition alignment became more than an observational opportunity. It became a test, a chance to separate geometry-driven brightness changes from intrinsic variability. A moment when, if the dust scattering followed predictable physics, the opposition surge should provide an independent constraint on albedo and grain structure. And if it didn't, if the surge was absent or present but anomalous, that, too, would be an answer. The investigation began to widen beyond the object itself and into the environment through which it was moving. The heliosphere, the bubble of charged particles and magnetic fields emanating from the sun, is not empty space. It changes constantly, shaped by solar wind speed, density fluctuations, and the heliospheric current sheet, a rippling boundary where the sun's magnetic polarity reverses. Charged dust particles around a comet can be influenced by these fields. Tails can twist, coma brightness can vary, scattering properties can shift, sometimes without producing strong gas signatures visible in traditional spectroscopy. This doesn't explain everything, but it offers a physically grounded hypothesis. What if the weirdness in 3 Atlas is not only intrinsic to the object, but also a product of how sunlight, plasma, and dust interact around it under specific solar wind conditions that happen to be unusual during its passage through the inner solar system? Researchers began cross-referencing the object's brightness and spectral changes against space weather data. Solar wind velocity from Parker Solar Probe, magnetic field measurements from near-Earth satellites, heliospheric current sheet crossings predicted by models. The goal was to test whether some of the variability could be environmental rather than geological, whether the instrument was, in a sense, the entire solar system. This shift in perspective reflects a broader evolution in how interstellar objects are studied. After Oumuamua and Borisov, the field learned that assumptions are costly. Models built on solar system comets and asteroids may not apply cleanly to objects formed in protoplanetary disks around other stars, with different temperatures, different volatile inventories, different radiation histories. 3 Atlas arrived from interstellar space at 57.7 kilometers per second, faster than either of its predecessors. Its trajectory suggests it originated from a star system with a high relative velocity, possibly ejected during planetary formation, or scattered by close stellar encounters. The dust it sheds is material formed around a distant star, condensed in conditions we can only infer. And so the watch is not just about cataloging an object. It's about reading a message written in physics. What can interstellar dust tell us about stellar systems we will never visit? What can non-gravitational accelerations reveal about volatile compositions in other protoplanetary disks? What can the absence of certain molecules teach us about surface processing during millions of years of travel through the interstellar medium, bombarded by cosmic rays and bathed in the faint glow of distant stars? The methodological shift has been as important as the technical one. Instead of treating each observation as a standalone snapshot, the campaign prioritizes cadence, redundancy, and independent verification. Photometry is cross-checked between multiple observatories. Spectroscopic reductions are performed by different teams using different pipelines, comparing results to identify systematic errors. Astrometric baselines are extended to confirm or refute tiny accelerations that sit at the edge of detectability. The emphasis is not on capturing a beautiful image or announcing a discovery, but on building a coherent picture from constraints, detections, and non-detections alike. This is the new discipline of watching. More humility, more patience, more attempts to break one's own interpretations before publishing them. It reflects a cultural recognition that interstellar visitors punish assumptions and reward caution. The January 22nd alignment will serve as a test of that discipline. High-precision photometry in multiple broadband filters, B, V, R, I bands, will track the phase curve as the angle sweeps below 2 degrees and back out. Polarimetry, if achievable at magnitude 16.7 with meter-class telescopes, will provide an independent constraint on grain structure and multiple scattering. The predictions are testable. If the dust is carbonaceous and compact, like that measured around comet 67P Churyumov-Gerasimenko by the Rosetta spacecraft, the opposition surge should show an amplitude around 0.15 magnitudes, with a very dark albedo near 3.4%. If the dust retains significant ice fragments, as some models suggest based on the extended antitail, the albedo could be higher, 10 to 30%, and the surge broader and brighter. If the dust is composed of fluffy fractal aggregates, pristine material from the interstellar medium, the surge width could span tens of degrees rather than a few. The measurements will not be easy. Weather gaps, telescope availability, and the faintness of the target, requiring apertures larger than 1 meter for precise work, mean coordination across multiple sites is essential. But the window exists. And unlike Oumuamua, which vanished before its nature could be determined, or Borisov, which never aligned at opposition, 3 Atlas is giving the community a chance. Beyond the immediate observations, the campaign has identified next-step discriminators, deeper searches at wavelengths, sensitive to carbon monoxide and carbon dioxide, which could explain the brightness without visible light gas emissions, improved rotation state constraints to test whether the light curve variability is rotational or intrinsic. Astrometric baselines extended into 2027 and 2028, long enough to confirm whether the non-gravitational acceleration is steady, decaying, or episodic. Some teams are preparing proposals for space-based infrared observations, where thermal emission from the nucleus can separate dust from gas contributions and estimate the true size of the object. Others are refining models of dust evolution, how interstellar grains might evolve during millions of years in the cold, irradiated void, and whether that evolution could produce the unusual scattering and polarization properties observed in 3 Atlas Dontao. The questions are multiplying, but they are becoming more precise. And precision in science is progress. What makes this watch unprecedented is not solely the technology, though coordinated networks, rapid data sharing, and multi-wavelength coverage are far beyond what was possible even a decade ago. What's unprecedented is the behavior, the recognition that interstellar visitors are rare, fleeting, and unforgiving of missed opportunities. The commitment to treating uncertainty as part of the data, not a failure of the method. The willingness to say, publicly and clearly, we do not yet understand this, and to keep watching anyway. In the weeks since December 19th, images of 3I Atlas have been captured by 8 different spacecraft, satellites, and telescopes. Hubble, the James Webb Space Telescope, the Subaru Telescope, the Very Large Telescope, Gemini North, and others. Each image adds a pixel to the mosaic. Each spectrum refines the constraints. And in the aggregate, a picture is forming, not of an alien artifact or a dramatic anomaly, but of a visitor that is different in subtle, persistent ways that demand explanation. The story holds its tension because the object is not finished with us yet. As it recedes outward, crossing 4.0 February, 6.0 by summer, the brightness will fade below magnitude 20 by late 2026, pushing the limits of all but the largest telescopes. But the motion will continue, the astrometry will accumulate, and the questions will sharpen. By 2027, 3I Atlas will be 16.0 from the Sun, magnitude 24, requiring the Hubble Space Telescope or ground-based instruments with adaptive optics to track it. By 2028, at 28.0, it will be magnitude 25 and approaching the edge of detectability. But even then, the data will matter, because interstellar objects don't come often. And every measurement we make, every detection, every upper limit, every contradictory data point is not just about one visitor. It's about building a framework for understanding all the visitors that will come after, and all the systems they came from. 3. Atlas reminds us that nature doesn't have to be dramatic to be profound. Sometimes the deepest mystery is a small mismatch that refuses to disappear. The scientific method is not a machine for instant answers. It's a discipline for living with uncertainty without turning it into a story that's too neat. If this object is ordinary, if its contradictions resolve into measurement error, instrumental bias, or compositional quirks within the bounds of known cometary physics, the watch will prove it with patience and data. If it is unusual, if its behavior points to something genuinely different about interstellar matter or the physics of small bodies ejected from other stellar systems, the watch is how we earn the right to say so responsibly, with evidence that survives scrutiny. Either way, the unanswered questions matter. They sharpen the tools we'll use on the next visitor from another star. They refine the models we'll test against solar system objects. They teach us how to watch the sky not for what we expect, but for what we don't yet understand. And in the quiet of all this careful attention, the cosmos stays what it has always been, larger than our certainty, more subtle than our instruments, and endlessly generous with surprises we can only interpret if we're patient enough to keep watching, even when the answers refuse to arrive on schedule. The alignment on January 22nd is not an ending. It's another data point, another measurement, another careful step into the unknown. Scientists are watching 3I Atlas like never before, not because they know what it is, but because they know how rare it is to have the chance to find out. And that chance, narrow as it is, must not be wasted.